Okay. In this lecture, we'll be discussing Fourier series representation. We know that Fourier series expansion is used for periodic signals only. Okay. And while as Fourier transform is used for non-periodic signals, we have discussed it in our some previous lecture also. In fact, we had drawn a table there. Okay. So this is in connection to that table that we have already drawn. So we'll discuss Fourier series representation of periodic signals. A periodic signal, it could be discrete time signal or it could be a continuous time signal. Okay. So let us assume that we have a signal first, okay, which is a discrete time signal. So if we have a signal which is x of n, okay, which is a discrete time signal, which is a discrete time signal, which is a discrete time signal, which is a discrete time signal. And for since the signal is periodic, it has fundamental period which is equal to n, okay, because it is discrete time, it is not continuous, so it has fundamental period equal to n, okay. Then the Fourier series of x of n is represented by, we'll say then x of n in Fourier series, it will be represented as by, I'll say, by a term which is known as discrete time, because it is discrete signal, discrete time Fourier series, okay. So what is discrete time Fourier series? It will be x cap of n. X of n was the signal, and x cap of n is the Fourier. It is the discrete time Fourier series representation of the x of n, and it is equal to summation of k a of k e raised power j k omega 0 n. Okay, I'll explain every term what is here. Whereas in this term, what is omega naught? Omega naught is actually fundamental period. Okay, omega naught is fundamental period, and it is equal to 2 pi by n. जैसे वहाँ continuous time in our continuous time signal we used to say it is 2 pi by t. Omega naught there used to be 2 pi by t. We have here 2 pi by n because we have n samples. We have n samples in the signal. Okay. So 2 pi by n, omega naught equal to 2 pi by n, it is the fundamental period. Okay, it is known as fundamental period. Sorry, it is fundamental frequency, not period. It is fundamental frequency of x of n. Of x of n. Okay, so let me write it here. It is fundamental period of x of n. Okay, fundamental period of x of n. So what is omega naught here? Omega naught, it is fundamental frequency, not period. It is, what is omega? Omega is frequency. In continuous time domain, we used to say omega is frequency. Similarly, in discrete time domain, we have a different omega here. Omega naught is fundamental frequency, not the period. So omega naught is 2 pi by n, 2 pi by n, which is the fundamental frequency. Okay. I'll give you an example of what is fundamental frequency. I'll describe it using certain graphs also. Okay. Just bear with me for some time. Now see, this is the fundamental frequency. Fundamental frequency. If we assume that there are many sinusoids present in the signal, if we assume there are many sinusoids present in the signal, okay, a signal can be it can be monotonic, or it can be a simple signal, or it can be a composite signal, which is also known as multi-tone signal. It means that the signal has many sinusoids inside. Okay, it has many sinusoids inside. So it's not a pure sine wave, it has many sinusoids inside. I'll show you later on graphically what does it mean. So we'll say So if it has many sinusoids inside, the frequency of the frequency of kth sinusoid, because it has many, if we assume that the signal is composite and it has very sinusoid, very different amount of sinusoids present, then the frequency of kth sinusoid is k times omega naught. Okay, because the signal is still periodic, we should remember that it is still periodic. Then the frequency of kth sinusoid is k times omega naught. Okay, and each of these sinusoid each of these sinusoid has a common period. It has a common period which is equal to n. ठीक है, आप इसको बस लिखें, मैं आपको बाद में I'll show you graphically what does it mean. So this is all about representation of Fourier series. Fourier series representation of discrete time signal. But if the signal is not discrete time, if it is continuous, okay, if the signal is continuous, then it will be represented by x of t, not x of n. Above we have shown it by x of t. But if it is continuous, if x of t is a continuous time signal, okay, of fundamental period equal to t, fundamental period equal to t, then we represent Fourier series representation would be, we represent then we represent x of t by the Fourier series representation. Okay, Fourier series representation. What is Fourier series? Fourier series of a continuous time would be x cap of t. So x cap of t is nothing but it is Fourier series representation. So we are studying Fourier series representation of periodic signals. Or periodic signals could be discrete time or they can be continuous time. So I have shown you first discrete time signal, how it is represented in the form of Fourier series. Then we are now I'm mentioning how a continuous time signal is mentioned using Fourier series. Okay. So x cap of t means the Fourier series representation of x of t, which is equal to summation of a of k e raised to power j k omega naught t. Okay, omega naught t. So we have a different omega here. Discrete time, in discrete time, the omega was like this, but in continuous time, the omega is like this. So it is just a representation. It doesn't matter. Okay, it is just a representation. We can mention it. It is a convention to show omega of discrete time signal in this shape, and for continuous time, the omega is like this. Okay, it's just a representation. So what is omega naught in this signal? Where omega naught is the fundamental frequency. It is equal to 2 pi by t. We know that. It is the fundamental frequency. Like we have studied fundamental time period of a signal. If we take inverse of the fundamental time period, we obtain fundamental frequency. So it is the fundamental frequency of the signal, which is x of t. Okay. And similarly here, frequency of kth sinusoid. Okay, kth sinusoid. What does a sinusoid mean? I'll tell you briefly after some time. And the frequency of kth sinusoid is here k times omega naught. Because when you have k equal to 1, it means you have fundamental frequency. K equal to 1 would mean fundamental frequency. Because here, if you see, what is the value of k here? K is 1. Okay, k is 1. So k times omega naught. So जब k का value 1 होगा, it means fundamental frequency. But if you have some other frequency, that means a kth harmonic or kth sinusoid. So what is the frequency of that kth harmonic? It is k times omega naught. Okay, I'll summarize this entire discussion with the help of certain graphical representation, you'll have a clear picture there. Okay. So the frequency of kth sinusoid is k omega, and each sinusoid has common period, and each sinusoid has common period which is equal to t, equal to t. Okay. And you should remember, uh, in composite signals, in multi-tone signals, which do not have just one frequency component, if they have many frequency components, every frequency component would be called a sinusoid component. Okay, so each sinusoid, a sinusoid whose frequency is an integer multiple of is integer multiple of a fundamental frequency. Okay, so every sinusoid, the frequency of every sinusoid is always integer multiple of fundamental frequency. What does that mean? That means that if you have a fundamental uh, sinusoid, it means its frequency will be 1 times omega naught. Okay, if you have a third sinusoid, it means its frequency will be 3 times omega naught. If you have a 10th sinusoid or 10th harmonic, its frequency will be 10 times omega naught. Okay, uh, so a sinusoid whose frequency is an integer multiple of fundamental frequency, it is known as, it is said to be a harmonic of the sinusoid. So what is a harmonic in the signal? Harmonic means a sinusoid which has the fundamental frequency integer multiple of, its frequency is integer multiple of fundamental frequency. Okay, I'll show you that in the form of graphical form. Suppose we have a signal like this. Okay, I'll draw the signal here. Say for example, we have a signal like this. Please try to understand this carefully. And the signal, it was actually a square signal. Okay, it was a square wave. It is deemed to be a square wave. So this is my signal. Okay, this was the amplitude should have been like this. So actually it was suppose we were supposed to have a sinusoidal wave, but in practical sense the wave is like this. Now if you will try to find the frequency response of this wave, its frequency components, if you will try to find its frequency components, this is what we will be having. Okay. This wave, it is actually, it looks like a square wave, but it is primarily made up of many different sinusoids. Please remember, every square wave has infinite number of sine waves inside it. Okay, since this is the time period, it seems to be the time period of this wave. So this is actually the time period of that sinusoid which is known as fundamental sinusoid. So this wave will be made up of many smaller sinusoids. Okay, infinite number of sinusoids. I'll draw a few of them here. So this is its composition now. So one of the composition would be this one. So it will have many sinusoidal waves. First wave, which is the most powerful wave and which is the most dominant one, it will have highest amplitude. उसका amplitude इसमें सबसे ज़्यादा होगा. This wave or this component, frequency component, it is known as fundamental tone, or it is known as fundamental harmonic. Why? Because it is the most powerful harmonic. It is the most powerful frequency component. And whatever is the time period of fundamental harmonic, that is actually the time period of your wave. Okay. Rest of the non-idealities that are present inside the wave, those are these, non-idealities. They are due to the presence of higher harmonics. Okay. So this is the fundamental harmonic. Please remember that fundamental harmonic has always the lowest frequency. And higher harmonics, which are always undesirable sometimes in the frequency, they have higher frequencies. So obviously the time period here, it is same as the wave. So let us draw the next harmonic. What is the next harmonic? So if the time period here is T naught, if the time period is T naught,
सर ये रिपीट कीजिए.
हाँ मैं इसको करूँगा, कोई बात नहीं है. यू जस्ट आप इसको सुनो आराम से, मैं इसको दोबारा से एक बार बताऊंगा, बट लेट मी फर्स्ट complete the sentence. Okay.
Okay, sir.
So the second harmonic would be something like this. I'll draw it like this. Now, if you see, what is the time period of the second harmonic? इसमें दो चीजें हैं. एक तो सेकेंड हार्मोनिक का एम्पलीट्यूड कम है, ठीक है, इसका एम्पलीट्यूड कम है. दूसरा जो इसका टाइम पीरियड है, it is from this point to this point. Okay, this point to this point. So the amplitude, so the time period of the second harmonic, it is 2 times the fundamental. Uh, it is 2 times the fundamental harmonic, or the frequency of the second harmonic. It is 2 times. Okay, it is 2 times, and the period is half. Period is actually half. So I will say like this: if you have this frequency component, which is the fundamental one, that is here, I'll draw here something. So F, this is the frequency which is fundamental frequency. Okay, F, iski frequency hai F. Say for example, its frequency is F. It is fundamental. The second component, which is represented by blue, its frequency is 2F. So it is a higher harmonic. Iski frequency higher hai. So its time period will be half. Okay, so time period is naturally half. It is shown here. If I will draw the third harmonic now, so let me complete first the second harmonic. I don't know why my device is not working properly. कुछ ऐसा होगा ये, ठीक है. अब let us draw the third harmonic now. For third harmonic, let me draw it with the help of green. For third harmonic, the frequency should be integer multiple. Okay, let us draw that its frequency is 3 times. 3 times. So for 3 times, you have to draw 6 cycles. So one will be like this. So this is the third harmonic. Okay, third harmonic. तो ये third harmonic जो है, if you understand this, इसका amplitude इतना है. Second का amplitude जो था वो थोड़ा higher है. Okay, its amplitude is for second, it is say for example this. For first harmonic, the amplitude is this. So definitely this amplitude is higher, ये उससे कम है, okay? Then this is still lesser, okay? So the highest amplitude you have is for the red wave or the red wave. Now if I will draw it like this, अगर यहाँ पे अब दिखाया जाए, so I can say the third harmonic की जो frequency it is 3 times f, okay? तो ये तो है टाइम रिप्रेजेंटेशन, टाइम डोमेन में अगर इसको रिप्रेजेंट करेंगे. अगर इसी चीज को हम फ्रीक्वेंसी डोमेन में, इफ वी विल रिप्रेजेंट दिस कंपोजिट सिग्नल इन फ्रीक्वेंसी डोमेन, हाउ वी कैन रिप्रेजेंट इट, ओके? अगर हम इसका फ्रीक्वेंसी स्पेक्ट्रम बनाएंगे, और स्पेशली एम्पलीट्यूड स्पेक्ट्रम, नॉट फेज स्पेक्ट्रम. If we draw the amplitude spectrum, you will have three frequency components, okay? One will be red, that will be f. Another would be blue one, that will be, say for example, twice f. The third one would be green, okay? This will be 3 times f, okay? Now see, for fundamental frequency, the amplitude is quite higher. For fundamental frequency, the amplitude is quite higher. Say for example, the amplitude is a naught, okay? So amplitude is here quite higher. For the second frequency component, for the second frequency harmonic, the amplitude is little bit lesser, okay? Say for example, it is a1, okay? This is here. Say for example, this is here a1. For the third frequency component, it is still lesser. Say for example, a2, okay? The third frequency component, उसका जो amplitude होगा, वो होगा उससे और कम. अब देखिए, इस amplitude spectrum में, which frequency component is more significant? Which harmonic is more significant? That is obviously F, the first one, red one. Why? Because its amplitude is much higher. Its amplitude is very high. It is powerful component. तो जो ये पूरी सिग्नल, जो कंपोजिट सिग्नल, ये वाली ऊपर जो आपके पास है, the signal that you have at the top, which is the composite signal, the impact of fundamental component or fundamental harmonic will be much more in the composite signal. So the period of the composite signal will be largely decided by the fundamental component. Whereas the impact by second harmonic will be lesser, and even third harmonic will be lesser. Even if we assume that we have another harmonic here, which is very, say for example, 10th harmonic, whose frequency is 10 times f, the impact of 10th harmonic on the signal will be nearly negligible. Why? Because the amplitude is very small. That is why in communication sometimes we say that we can neglect higher harmonics in the signal, higher harmonics. So please remember that all of these are harmonics. This is first harmonic. It is first harmonic. This is second harmonic. And this is third harmonic. Third harmonic. This is 10th harmonic, or I will say higher harmonic. Okay? तो ये harmonics कैसे पहचाने जाते हैं? Please remember that the frequency of harmonics is always integer multiple of fundamental frequency. What is the fundamental frequency? It is f. What is the frequency of harmonics? It is either 2f, it is either 3f, 4f, 5f, 10 times f, 100 times f. जितना higher harmonic होगा, उतना ही उसका integer multiple frequency होगी. That's what I said. A sinusoid whose frequency is an integer multiple of fundamental frequency, okay, or fundamental harmonic, is said to be a harmonic. It's said to be harmonic. Even I have already shown you frequency of kth sinusoid. That means frequency of kth harmonic is k times omega naught. Okay, this is 10th harmonic. What is the frequency? It is 10 times f or 10 times omega naught. Okay, that is why I wrote there that frequency of higher harmonic or kth harmonic or kth sinusoid is k times omega naught. And each sinusoid has common period equal to t. Okay, in सबका जो common period होगा, please remember here, what is the time period of this signal? This signal you have here, the time period is t naught. Okay, what is the time period of blue harmonic? It is t naught divided by 2. Okay, what is the time period of green signal? It is t naught divided by 3. तो इन सब में कोई चीज कॉमन है, पीरियड तो कॉमन है. What is the common period? What is common term in them? It is t naught, fundamental period. That is what I am saying, that Each sinusoid has a common period equal to t. What is the t? T is fundamental period of the signal. Okay, it is fundamental period of the signal. अगर किसी बच्चे को कोई confusion है, कोई question है, please ask me. Do you have any question? Roll number 78 is here.
Yes, sir.
कोई question तो नहीं है बेटा, आपको ये समझ में आया?
Yes, sir.
What about Bushra?
जी
14?
सर।
कोई question है बेटा? क्या सवाल है, पूछो.
नो सर, समझ आया।
हम्माद, roll number 12.
यस सर, सर नहीं आ गया समझ।
Okay, और किसी को कोई सवाल तो नहीं है? I think this is clear. तो कभी कभार once I go into the theoretical discussions, you should wait for some time. I'll definitely give a better explanation for that. So please remember, from now onwards, every signal, say for example this signal, okay, I have this signal now. I don't know how this signal look like, but definitely this is not a pure sinusoidal signal. This is not a pure sinusoidal signal. It is a composite signal. इसमें बहुत सारे sinusoids होंगे. We don't know how many harmonics will be present there. But it is always wise that in communication we say that we can neglect higher harmonics. Okay, we can neglect higher harmonics. Sometimes in communication we say we can neglect higher harmonics. Why do we neglect higher harmonics? Because their impact in the signal is negligible. Why? Because their amplitude is very small. Although their frequency there is some frequency component, lekin their amplitude is very small. So overall impact on the composite signal. This is a composite signal. A composite signal is a mixture of many sinusoids. Okay, a composite signal is mixture of many sinusoidal signals. So the distortion that you have here, it is because of sinusoids. If you keep on increasing the higher harmonics, this sinusoid signal or this composite signal will be a little bit like this. Okay, it will become more smoothened. When you have entire square wave, it means the number of harmonics is infinite. Okay, it means the number of harmonics is infinite. As you go on neglecting the harmonics, जब आप harmonics को higher harmonics को neglect करते जाओगे, higher harmonic, third harmonic, second harmonic को neglect करोगे, you'll be only left with fundamental harmonic. What is the shape of fundamental harmonic? It is sinusoidal. तो एक स्क्वायर वेव में जितने भी आप हायर हार्मोनिक्स नेग्लेक्ट करते जाओगे, the more you will neglect the higher harmonics, the more it will tend to become pure sinusoidal. Okay, the more it will tend to become more sinusoidal. And if in a sinusoidal wave you keep on adding harmonics, first harmonic, second harmonic, third harmonic, and you keep on adding to infinite level, to infinite number of harmonics, then it will tend to become a square wave. It will tend to become a square wave. Okay, I think it is more than sufficient, this explanation for these lines, whatever I have mentioned here. Okay, so I would repeat the term. A sinusoid whose frequency is an integer multiple of a fundamental frequency is said to be a harmonic of the sinusoid. Okay, so we can now say then, thus in our context, whatever we are writing, thus if we represent a signal, in sinusoidal form, thus we can say e raised power j k omega naught, e raised power j k omega naught is nothing but it is the kth harmonic. It is the kth harmonic of a signal which is e raised power j omega naught. Okay, तो मान लीजिए e raised power j omega naught is a sinusoidal signal. It is a sinusoidal signal. Okay, it is a sinusoidal signal. But if you write down e raised power j k times omega naught, it means it is a kth harmonic of this signal. Okay, this sinusoid signal. So we are representing complex sinusoids. हमने पीछे भी जो discussion किया था, we were discussing complex sinusoids. Okay, so signals which are complex and sinusoids. Now in this term we are now left with ak. What is ak? Okay, a of k. Whereas a of k is the weight of applied kth harmonic. जो harmonic है उसका weight means amplitude. इसका amplitude कितना है? So it is the weight applied to kth harmonic. So it is the weight applied to kth harmonic. Okay. And the hat cap denotes the approximate value. That is, or I can say the Fourier series representation. The variable k, what is k here? The variable k indexes the frequency of sinusoids. It means that if k is equal to 1, it means fundamental frequency or first frequency component. If k is equal to 2, it means the second frequency component or second harmonic. If k is equal to 3, it accordingly means the frequency component, which frequency component you are talking about. Okay, so जो k है ये denote करता है kth harmonic. So its value can start from 0 to or 1 or 0 to 1 to n if you have n harmonics inside your signal. Okay, so in general we say that in particular, or in particular to this discussion, we say that the complex sinusoids, which are represented by e raised power j k omega naught n, which is actually the kth harmonic, are n periodic. Okay, n periodic means they are n times periodic. They have their frequency component is n times the fundamental frequency component, n periodic, in the frequency index k. In the frequency index k, and is shown by relationship like this. See, if you have a frequency component e raised power j n plus k, तो इसको कैसे हम represent करेंगे? It will be written as e raised power j. If it is n periodic, it means you have n, or we can simply go by expanding these two terms, j n omega naught n, okay, into e raised power j k omega naught n. Okay, if we have exponential like in this form, then we can expand that term in this fashion. This can be written as e raised power j. Instead of n pi, we can write down n omega, we can write down 2 pi. Okay, I'll show you why we'll write down 2 pi. So this can be written as e raised power j 2 pi n into e raised power j k omega naught n. Why? Because we have already mentioned at the top that omega naught, somewhere here, omega naught is the fundamental frequency. Okay, omega naught is fundamental frequency. What is omega naught equal to? It is equal to 2 pi by n. Okay, so we can write down n times omega naught, it is equal to 2 pi. N times omega naught is equal to 2 pi. So we can substitute it in the equation above. So this is where we will be obtaining it. And we also know that e raised power j theta, को जब plot करेंगे, okay, its magnitude is always equal to unity, and angle can change. Angle can change from 0, or it can change from pi by 2, or then it will be pi. Okay, then it will be 3 pi by 2, or it will be 0 or 2 pi. So 2 pi and 0 are lying at the same point. So therefore we can write down this e raised power j2 pi n will be equal to e raised power j 0 n. Okay, so that is e raised power 0, that will be equal to 1. Okay, तो अगर हम इसको यहाँ substitute करेंगे, we will have now e raised power j n plus k into omega n will be equal to, I'm rewriting this equation again. So it will be equal to e raised power 0 into e raised power j k omega naught n. Okay, so that will be equal to e raised to power j k omega naught n. Omega naught n. Okay. So we can write down hence there are only n distinct complex sinusoids of the form of e raised to power j k omega naught n. Omega naught n. ठीक है, j k omega naught n. Basically, this Fourier series, we have two different forms of Fourier series. Okay, I would like to first mention it here. The expansion that I'm discussing here, it is known as exponential Fourier series expansion. Okay, so before I will extend this discussion more, I would first like to mention the types of Fourier series expansion. Types of Fourier series expansion. Fourier series किस तरीके से लिखी जाती है? How it is represented? There is a form which is known as trigonometric Fourier series expansion. This is also written for periodic signals. ठीक है? Trigonometric Fourier series expansion. The second one is known as exponential Fourier series expansion. जो हम इस वक्त discuss कर रहे हैं, it is exponential Fourier series expansion. But I'll mention the trigonometric also. Okay. In trigonometric Fourier series expansion, you write down for a continuous time signal, you write down x of t cap will be equal to a naught plus summation of n equal to 1 to infinity, because there are infinite, we assume that the signal is having infinite of harmonics, infinite number of harmonics. So it is considered as summation of sine and cosine terms. Okay, it is a raised power n cos omega t plus b raised power n sine omega t, sine omega naught t. So the entire philosophy behind this equation is a signal could be either, it could be if it is an AC signal, it could have certain DC component. Okay, so this is, please remember that A naught is the DC component. ये हमने पहले भी signals and systems में देखा था. If you do not have an AC component, you have a term, you have a DC value 2, 4, 3 or any other whatever you have. So that digit or integer would represent the DC value of signal. Okay, so this is A naught. तो इसमें हम एज्यूम करते हैं कि सिग्नल्स में कहीं ना कहीं डीसी कंपोनेंट होगा और फिर उसमें एसी कंपोनेंट होगा, और वो एसी कंपोनेंट साइनोसाइडल होगा, या तो वो साइन वेव से बना होगा या तो वो कोसाइन वेव से बना होगा. ठीक है, तो दैट इज व्हाई वी हैव टू टर्म्स, सम कोसाइन कंपोनेंट एंड सम साइन कंपोनेंट. So x of t is assumed to be made up of three components here. One DC component, which is A naught. A naught can be 0. It is not necessary. It is average DC value of a signal. If it is not present, then it would be equal to 0. Sometimes other components are also equal to 0. अगर signal खाली sine wave होगी तो cosine component उसमें 0 होगा. But this general representation would mean that a signal is made up of a DC component and certain AC component. Now the AC component could be complex. It could not be very simple. It can be, of any form. When it is a composite signal, then it might have certain cosine components and certain sine components. So that is why we write down, and that frequency components may vary from n equal to 1, 2, 3, 4 up to higher components. ठीक है, तो इसमें higher harmonics भी present हो सकते हैं. When we write down summation of n equal to 1 to infinity, it means we are summing up from 1. 1 means the fundamental harmonic, up to infinity means we do not know what is the type of signal. We are assuming that the signal has infinite number of harmonics. Now each harmonic may be a sinusoidal or it may be a cosine wave. If it is sine wave, then say for example you have a second harmonic n equal to 2. ठीक है, अगर n होगा equal to 2, तो अगर second harmonic होगा, if you have second harmonic, then b, और आपको पता है वो sinusoidal है, then b2 will be equal to some finite value. It will be some integer. Okay, अगर आपको पता है कि second harmonic में cosine value नहीं है, तो उस वक्त an will be equal to 0. So this is how it is being expanded. I'll definitely explain this. But we should remember that here a naught is DC value or average value of x of t, average value of x of t, DC value or average value of x of t. And it is also calculated, or it is calculated by 1 by t naught integral of t naught x of t dt, x of t dt. ठीक है, this is the average value of x of t. Similarly, we have formulas for a of n किसके बराबर है? A of n is the constant. It is equal to 2 divided by t naught integral of over the period, over complete period, because these are all periodic signals. The discussion is all about periodic signals. So we integrate the signal over one complete period or one t naught. So x of t into cos of n omega naught t, okay, dt, and bn is equal to 2 by t naught integration over one complete period x of t sine n omega naught t. While as omega naught, you know what is omega naught? This is the fundamental frequency of the signal. X of t is the signal. And what is t naught? T naught is the fundamental period. Okay, so this is one we will not हम इसमें ज़्यादा अभी discuss नहीं करेंगे. But the second one we were basically discussing the exponential Fourier series expansion. Okay, what is exponential Fourier series expansion? Exponential Fourier series expansion. In exponential Fourier series expansion, a signal is always represented by summation of n equal to minus infinity to plus infinity. Although I have not described it here from minus infinity to plus infinity, I have shown it from k, okay? K, summation of k. So I was trying to explain what will be the value of k. So I'll postpone that discussion before I discuss this thing. So I was showing there, I have written there a of k. We can write down c of n or a of k. It is one and the same thing. A of k is a constant. A of k means it is a constant or a weight of the frequency component which is dependent on k, or which is dependent on frequency. Similarly, c of n is just a representation. It is also dependent on frequency. So a of k, या आप इसको c of n लिखें, it is one and the same thing, okay, into e raised power j omega naught nt, okay, j omega naught nt. That is what we were writing before also, where here c of n is a complex exponential Fourier coefficient. आप इसे Fourier coefficient कहें या आप इसको weight कहें, it is one and the same thing. There is no problem in that. यहाँ तक अगर किसी बच्चे को कोई सवाल है, you can ask me. Please ask me if you have any question. Rizwan is here, roll number 27.
जी सर.
बेटा आपको ये discussion समझ में आया?
हाँ सर.
So we are discussing exponential Fourier series expansion. ठीक है, हम उसी को discuss कर रहे थे. I forgot to mention the types initially. What about Taruba is here, 67. कोई सवाल है आपको? तरुबा?
Yes, sir.
हाँ बेटा, आपको समझ में आया ये?
Yes, sir.
Okay. Roll number 54 is here.
Yes, sir.
हाँ बेटा, आपको बेटा समझ में आया ये?
जी सर.
Okay, all right. ठीक है. So we were discussing exponential Fourier series expansion. Okay. Fourier series expansion. Okay. ठीक है. So I said that there are only n distinct complex sinusoids of form of e raised power j k omega naught. Okay, anyway, I think this is not important here. uh, why we are giving limits from n equal to minus infinity to plus infinity? We are actually assuming that in a discrete time signal, okay, in contrast to discrete time signal, if we assume that this is a continuous time signal, in contrast to discrete time signal, continuous time signal will have complex sinusoids with distinct frequencies and they will be continuous. ठीक है, इसमें infinite number of frequency components होंगे. In discrete time signal you have finite values. आपको एक sample यहाँ होगा, एक sample यहाँ होगा, एक sample यहाँ होगा. So you have finite signal components. But in continuous time signal, since the signal is continuous, okay, there are, say for example, you have a composite signal like this. Since the signal is composite and it is continuous, there will be infinite number of frequency components. Okay. So here there are potentially infinite number of distinct terms in the series. Hence we write down, k or n equal to minus infinity to plus infinity. Anyway, I'll go on further explanation of this. My device is not working sometimes. Just give me a second. Okay. C of n is complex exponential Fourier coefficient, Fourier series coefficient. Okay, exponential Fourier series coefficient. So C of n is complex exponential Fourier series coefficient, Fourier series coefficient, and it is calculated, A of k or C of n इसको calculate किया जाता है by 1 by t naught integral over one period x of t e raised power j n omega naught t से. This is how we calculate C of n. So C of n is calculated by this term. Okay, so I'll solve a question. Maybe you'll have an idea how do we solve this, how do we calculate C of n. Yeah, जो ये terms है, it might be looking very strange to you. So I have an example. For example, here there is a signal. It mentions that determine Cn of signal. Okay, Cn of signal. What is signal? Signal is this one. This is basically periodic. Okay, it is a periodic signal. So you have 0 here. Then you have, say for example, this is tau by 2. And somewhere here it is t naught by 2. And you have here t naught. Similarly, you have minus tau by 2. Then you have minus t naught by 2 here. तो यहाँ कहीं है minus t naught. Okay, so the entire period is basically from 0 to t naught. If you will see, the signal is like this. तो ये सिग्नल एक साइकिल बनाती है. ठीक है, इसी तरीके से यहाँ से ऐसी है. तो ये सिग्नल, इसके बाद और भी है हाफ, इसके बाद और भी है हाफ. तो इतना एक ये बनाती है. It makes one cycle. It makes one cycle. Okay, ठीक है. Now Cn for this problem, it is also mentioned that the amplitude is A naught. इस signal का amplitude है A naught, and this is x of t here. Okay. we know that Cn it is equal to 1 divided by T naught integral of. Now see, since the signal is periodic, if you have odd signal or even signal, अगर signal odd है or even है, okay, the value of n basically, or the value of the period that we are taking, it is an arbitrary and may be chosen to simplify the problem. जब जैसी problem आपके पास होती है, it is chosen accordingly by exploiting the symmetries of the problem. So you choose the value of n or time period, या integration जो आप कर रहे हैं, integration का period जो है, if you choose it, please choose it in a way so that it can simplify your problem. You can exploit the symmetry of your question also. Okay, so in this question we can see what is the time period here. ठीक है, इसमें time period कहाँ से कहाँ तक होगा, तो या सिग्नल कहाँ से कहाँ तक प्रेजेंट है, उस हिसाब से हम इसको जो है लिमिट्स करेंगे. तो फॉर एग्जांपल द सिग्नल इज प्रेजेंट हियर बिटवीन दिस इंस्टेंट, यहाँ प्रेजेंट है इस एरिया में, although the period is from maybe from here to here, लेकिन इस जगह इस सिग्नल का वैल्यू कुछ नहीं है, इस जगह इस सिग्नल का वैल्यू कुछ नहीं है. तो जब हम इंटीग्रेट करते हैं, वी आर एक्चुअली समिंग द स्मॉलर पार्ट्स टुगेदर. ओके, so we will be taking the limits here minus tau by 2 to plus tau by 2. Why? Because the signal is present only there. One time period would also mean the signal between these 2 points. ठीक है, वो यहाँ से यहाँ तक. One time period would mean the green one also. तो उसमें भी हमें थोड़ा सा एक पार्ट यहाँ से लेना है. If we will take green one, तो हमें फिर सिग्नल को या तो एक थोड़ा सा पार्ट ये लेना है, and some portion will be taken from here. So there are two parts in green methodology. The calculation will become complex. So we will follow the blue one. ठीक है, उसमें जो सिग्नल जहाँ प्रेजेंट है वहीं पे हम इंटीग्रेशन करेंगे. So the limits will be minus tau by 2 to plus tau by 2. Why? Because the signal is present only there. And what is x of t? X of t here is a naught. Okay, it is a naught. Then you have same e raised power, it is probably minus j. Yes, it is minus j, it's not plus j. I have mentioned here, so it is minus j. E raised power minus j n omega naught t. ठीक है, जो equation a है ऊपर. So I am just writing the same equation. 1 by t naught integral of a naught and something with respect to t. Okay, if you integrate it, it will be 1 by t naught times a naught bahar aayega because that is a constant now. Then inside you will have e raised power, integration of e raised power x. Okay, so you will have e raised power x same minus j n omega naught t, और जो x का आपका कोफिशिएंट होगा ax, it is e raised power ax, integration of e raised power ax, वो आपका नीचे आएगा. So the coefficient will be minus j and omega naught is the coefficient. Okay, then you can apply the limits. Tau by 2 and minus tau by 2. These are the limits of the integration. Okay, so you can then write it like this. It will be